Now, we're going to resume with our presentation of quadratic formula and equations solved using that quadratic formula. Some equations are not quadratic, but are reducible to looking quadratic. I generally come to call these quasi-quadratic. Here's an example, a couple examples, okay? So here is this expression. This is a fourth degree polynomial expression, all right? And by doing a suitable substitution here, okay, if we let u stand in for x squared, then the equation appears quadratic in u, okay? So I generally call these type of things quasi-quadratic, okay? Here's another one of sorts, okay? This is to the 1/2 power. You might find that a little intimidating, but you need not, because we can just do a substitution. We can let the 1/2 power of y be u, okay? And then then if we square that, then we get u squared, and we get y to the 1/2 squared, which is simply y, okay? And again, this expression you wouldn't think of being quadratic, but with the suitable substitution, you see it does turn quadratic. So we're coming back and looking at some more examples of what appears to be quadratic and can be made a little bit more user-friendly in its appearance with a suitable substitution. Okay? So as I said here, at this point, the problems would be solved quadratically, either by factoring, which I think both of these would factor, and we've already done problems of that sort, so that's really nothing new to you, okay? But you got to remember that when you do a substitution, use a different variable, okay? So you don't think, oh, I've already solved this for y, and I'm done. Okay, let's look at solving this problem, okay? So with a suitable substitution, u standing in for x squared, it becomes u squared plus 12, u squared plus u minus 12, which is nicely factorable, offering you solutions in u, but let's not forget, we're not concerned with what u would be, we're concerned with what x is. So we have to come back, we have to replace the u with the x squared, okay? In this instance, x squared equals root 3. So then we take the square root of both sides and we get x equals the positive or negative root of 3. Over here, we get x squared equals negative 4. Easy to see that once you want to take the square root of both sides, you end up taking the square root of a negative, so that's not going to contribute any real solution, okay? You could have alternately factored it in this sense, okay? If you wanted to, just, you know, x squared plus 4 and x squared minus 3, and then those two factors set equal to 0 and solve, and you end up with the same solution, okay? Either way would suffice, okay? Here's another one. Here's the one you probably don't like. You don't like that half power. That's fine. Get rid of it, okay? Let the u value stand in as z to the 1/2. And again, if z is to the 1/2 is u, then z must be u squared, okay? So z to the 1/2 squared is u squared, okay? Or is z rather, okay? So then with that, we now have a nice quadratic. We now have a nice factorable quadratic. U minus 2, u equals 2, but it is z to the 1/2 is that the actual value of u. So then we have radical z equals 2. Squaring both sides, we get z equals 4. Okay, on this front, okay, we have u equaling negative 9, and then z to the, replacing is z to the 1/2, okay? as the value of u. We're coming down to the square root of z equals -9, squaring both sides. Okay, we get z equals 81. Now, anytime you're doing something of this, particularly when we started out with the equation being of a smaller exponent power than we actually turned it into, we really want to come and we want to check our solution. So altering the very nature of this equation from the start gives rise to suspicious solutions. So again, what we said, well, we said before, when we had this, was actually the highest power was 1, and so we might suspect that that has only one solution. Okay, so that's another aspect to keep in mind. Remember, we had said that the highest exponent in the equation is generally indicative of the number of solutions. Now this ended up giving us 2, but we changed the whole nature of the equation when we did this substitution. So we really want to come and we want to check those answers, the 4 and the 81. So we come over here, we put in the 4, and of course the half power means the square root, and that seems to strike up a balance. Now when we come over here and we put in the 81, the half power of 81 turns that into 9. That does not strike up a balance. Okay, so since the original equation was not quadratic and was altered in form, okay, in alternate form for simplicity of solving, and sorry about that, we should be suspicious of the solutions and check to see which one will satisfy and which one will have to be discarded. So in this instance, okay, we had to discard the 81. Okay. Certain equations contain radicals and can be expressed in quadratic form. Okay, so let's take a look at this expression. Okay, anytime you have a radical expression, your best protocol is to try to isolate that radical. Okay, so I chose to put the 4 on the other side. Now I'm going to square both sides, and I repeat what I just said. I'm going to square both sides. Okay, so both sides means not squaring individual pieces over here, but squaring this as a binomial. Okay, now the nice feature here again is that we're going to get rid of our square root in squaring that. Okay, but over here we get a trinomial. And lo and behold, this just unfolds to a quadratic expression, as you can see. Okay, so to that extent, we're going to see what we can do to obtain the solutions on this. I think it's going to factor. It does factor. It offers us 2 solutions in x, those being 7 and 2. I have to give some suspicion to one or the other of these because, again, initially my highest power was x to the first, which gives rise to me suspecting I'm only going to find one solution. So let's throw both of these back into the original expression and see if we get a balance. So here's our original expression. The value of 7 is replaced, and we keep the balance. When the 2 is replaced back in, we do not maintain the balance. Therefore, we have to toss away the one solution of 2, and we'll accept the solution of 7. Again, you altered the very nature of the equation to make it a little easier on yourself for solving. So to that end, you have to be suspicious of the solutions that result from your calculations. I think we're going to take a look at one more right here. Okay, this is a problem which is double roots. Okay, and double roots generally mean we have to square 2 times over. Okay, so so I'm going to, but to do that, I'm going to want to try to isolate. I can't isolate well, I have to isolate one root per side. That's what I'm going to do. So there's my first procedure. Now I'm going to square both sides, and again, I'm squaring both sides. I'm not squaring individual pieces. When this is squared, it does not come down to y plus 1. It comes down to, and here's a recall, the binomial square pattern. A squared, a plus b squared goes to a squared plus 2ab plus b squared. So bearing that in mind on the right side of this equation, you know, we get the a term squared and the b term squared, which means this is going to come down as y and 1. But then the middle term is twice the product of these two. So the product of these two is 1 root y. Twice that is 2 root y. So again, we still have a root in our equation. So we want to isolate that. So we can easily see we can lose 1 off of both sides, and we can subtract y off of both sides. So in doing that, okay, we now are left with having to square this again to solve for y. Okay, so let's see what happens when we do that. We square both sides again, and we get y squared equals the quantity of 2 root y squared, which is going to give us y squared is equal to 4y. That should lend itself to a factorable expression. Do not commit the algebraic atrocity of dividing by y. Okay, again, do not commit that algebraic atrocity. All right, so this goes to a quadratic expression. We're going to pull out y as a common factor, and factor this in this sense gives rise to 2 solutions. You should check the validity of both to see if they're valid. So in this instance, both of these check as viable solutions. Okay, both of these check to be viable solutions. Okay, and let's see, we have some fractional equations which are reducible to quadratics. Okay, so here we have this expression, which again, the very first thing you want to do is declare what r cannot equal. In this instance, it cannot equal 0 or -1. But we know we can clear out the fraction by multiplying by the common denominator. In this instance, the denominator of 2 times r plus 1. Okay, so there's what we say is our common denominator is 2r plus 1. We elect to multiply both sides of that equation by that common denominator, which will have the clearing out effect of the denominators. And again, you look at this expression times 1 over r, you lose the r, so you're left with 2 times the r plus 1. This 1 over r plus 1 is multiplying the common denominator. We lose the r plus 1, and we just pick up the 2r. Over here, the only cancellation is the 2's. So now, with multiplying through by the common denominator, we eliminate the denominators altogether and eliminate headaches in doing that. Okay, we simplify by doing some distributing. We notice that we still have an r squared. We still have the possibility of 2 solutions. So we're going to see what happens from this front. We come to this quadratic. We believe that this is going to factor, and here it is factored. We find our solutions in terms of r. Okay, we check to see if our solutions are not something we said we couldn't get. Okay, both of them seem to check in that. Okay, we did not significantly alter the nature of this equation, so therefore these solutions don't have to give rise to suspicion. Okay, and they are both valid solutions. The note here again is to say that if your solutions end up being something you already said it couldn't be, the red flag should go up and you should check that. Okay, let's take a look at another one. This one, the nice thing, one fraction on each side gives rise to simply cross multiplying. Of course, x can't equal 3. We need to make that statement from the beginning. Multiplying both sides by that is effectively cross multiplying, okay? Which gives rise to this expression, okay? Which we want to see is bring everything to one side. See if that's factorable. It is factorable. 9 out of 10 times your expression is going to be factorable. You should not have to resort to a quadratic formula, okay? There gives rise to simple equations from which we can find the solutions. And again, there's no significant alteration to the equation, so there's no reason to give rise to solutions that are suspicious. Okay, this was simply solved by pulling out the common factor. We noticed that we should get 3 solutions, and which is synonymous with the 3 x-intercepts of the graph. Okay. There we go. Okay, this should give rise to 4 solutions, and it actually gives us but 3 intercepts. As you can see there, it's nice and easily factorable. Okay, and the solutions are as we see. Okay, and again, the solutions will be at most 4, but in this case we only pick up 3. We pick up this solution at the origin, which is what we call a multiplicity, okay? Because it really doesn't go through the origin, it just kind of skims the origin, okay? And that's and we'll talk about that later, okay? Here's another interesting graph. This we suspect could have up to 4 solutions, but we end up only seeing 3. We have this other issue here of a multiplicity, okay? But there again, all right? The highest power is indicative of the maximum number of solutions that you could get. Okay, and so when we'll talk about more how we can find those solutions. Okay, so conclusions: the number of solutions to a polynomial equations is at most the highest power of the polynomial. Okay, these are what we look at with this is a polynomial graph, what we'll soon call a polynomial function. Essentially, if you let y equal 0, it collapses to an equation, okay? And the solutions to this equation are synonymous with the x-intercepts of the graph. When given a polynomial function of this form, we will be able to graph it, since when setting y equal to 0, we are finding where it crosses the x-axis. So that does it. I'm sorry this got to be a little long-winded. Okay, there's your conclusions again, but we covered a lot of ground on this, and hopefully you upload